Hi everyone, this is Mrs. G.A. and today we're going to talk about systems of linear equations in two variables. So if you have a system of linear equations that have two variables, you have three possible outcomes for the system. So one possible outcome is that you have two lines that essentially have the same slope and therefore will never cross, which means you have no solutions. And we call this type of system inconsistent. The second case is that they cross at exactly 1 point, and this just simply has one solution. And then the third case is that you actually have two equations that represent the same exact line. So in a case like this, we call that system dependent, and it means that there are infinitely many solutions. So there's actually a way that we can describe the relationship between x and y to give some sort of answer for these, even though there are an infinite number of answers. Okay, so we're going to do a really quick example for a system with one solution because we just did a full video on how to solve a system of two equations. So just really quick review. There's lots of different options we have to solve this. Maybe you want to use the elimination method. So I'm going to multiply our top equation by 2 on each side, and that will allow us to eliminate the y's. So that gives us 6x minus 2y equals 0, 5x plus 2y equals 22, and now we can add vertically. 11x equals 22, x equals 2, and then we can back substitute into either equation to help us find y. So let's use that first equation. 3 times 2 minus y equals 0, so y equals 6. Remember, we write our answer as an ordered pair. And again, a really quick way you can check your answer is by substituting both x and y into both equations. So if you do that into the first equation, you get 6 minus 6 equals 0, which is valid. And in the second equation, it gives you 10 plus 12 equals 22. So we can really quickly verify that our solution is correct. So again, this is a very normal system that has just one point of intersection. So now we're going to talk about what it looks like when a linear system has no solution. So if you look at this, again, we can solve this in a number of different ways. So for this one, if we use elimination again, we do need to multiply both equations. Maybe we'll try to eliminate the y's again. So we can multiply our top equation by 3. So that will give us a term here of negative 6. So that means that we can just multiply our bottom equation by positive 2. Let's rewrite our equations. 24x minus 6y equals 15. And negative 24x plus 6y equals 14. So if you add vertically, first thing you'll notice is that both x and y cancel out, which does not always mean no solution. So you have to see what we get. So that gives us 0. This gives us 0. So this gives us 0 equals 29. So since both eliminated and we ended up with a statement that's clearly not true, this is how we know that our system is no solution. So maybe you're thinking to yourself, well, how do I know if I actually did this problem correctly and didn't make a mistake? So if you remember from that first slide, no solution happens when you have two linear equations that have the same slope. So if you want to double check, you can actually rewrite both of these in slope-intercept form to see if they do have the same slope. So let's do that really quick. So for our first equation, I would just add 2y and then subtract 5. And then you can divide by 2. So we get 4x minus 5 halves. And then for the other equation, let's again put this into slope-intercept form. So let's add 12x to both sides. And then again divide by 3. And you can see that we do have two equations that have the same slope. So this is a nice way that you can verify that the solution actually, or the system actually does have no solution. Okay, so the last case is a system that has infinite solutions. Let's look at this one together. Again, let's start solving this using the elimination method. So maybe we multiply the top equation by 4 and then the bottom equation by -3. And then you'll see that we really are just getting opposite forms of the same equation. So for this, if I continued with the elimination method, we would end up with 0 equals 0. So here's, again, a case where both x and y eliminate, but since I end up with a statement that is true, this is how we know that it's infinite solutions. Or again, you can see here, these are really just different forms of the same exact line. So when you have infinite solutions, we're not really just going to stop there. We want to come up with a way to describe the relationship between x and y, and that can give us a sample or like a way to find possible solutions. So here's how you do it. There's actually two different ways we can write our answer. So first, you pick one of the variables. So let's call x equal to t. Okay, so we're going to set x equal to t. So I can take either equation. I'll take the first equation, and I'm just going to replace x with t. So we say 3t minus 6y equals 12. So now we're going to solve for y in terms of t. So I can add 6y to both sides and subtract 12. So we get 6y equals 3t minus 12. And again, I'm solving for y in terms of t. So we can divide both sides by 6, and we get y equals 1/2 t minus 2. So now that both x and y are in terms of t, this gives us a model. The model looks like this that can tell us possible solutions. So you can pick any value for t, and if you plug it into this formula, it gives you possible solutions. So for example, if I set t equal to 0, so this becomes 0, 0 times 1/2 minus 2 is -2, so that's a possible solution. Or let's say I set t equal to 4, so that becomes 4, this becomes 2 minus 2, which is 0. So using this model, or this framework that we created, it gives us a way to quickly generate possible solutions. Now, of course, we could also do the same by, instead of setting x equal to t, we can say let y equal t. Let y equal t. And again, I will replace y with t into either of the original equations. So let's say we use that first one again. So again, we're trying to rewrite both x and y in terms of that new variable t. And now we need to solve for x in terms of t. So we can add 6t to both sides and then divide by 3. So another way of writing this answer, you could say 2t plus 4, comma, t. So again, you could still plug in potential values for t, and you would just get a list of answers. So let's assume, again, t is equal to 0. Then it gives us that same coordinate that we got before, 4, 0. Or let's say we set t equal to -2. That would be our y value in this case. And then here, 2 times -2 is -4, plus 4 is 0. So again, it just gives us a framework that allows us to quickly find any number of those infinite solutions. So again, whenever you have a case where your x and y disappear, but you're left with a true statement, it's going to be infinite solutions, and you need to find a way to define x and y in terms of a new variable, usually t, which again provides a framework that you can use to quickly find as many points as you want from this system. And then just to reiterate, either of these answers are perfectly fine because they really represent the same thing. All right, why don't you go ahead and pause the video and give this example a try on your own, and we'll check your answers in just a few seconds. Okay, so here you can see I tried to start solving using the elimination method, and again, both x and y disappeared, but I was left with a true statement telling me it is infinite solutions. So again, we want to define both x and y in terms of a new variable. So if you set x equal to t, you should get this as your answer, t 1/3 t minus 4. Or if you set y equal to t, you would get the answer 3t plus 12, comma, t. And again, these are just a framework for you to be able to find coordinates that work for this system. Okay, so now we're going to move on to modeling systems of linear equations. So essentially some more application-based problems or word problems. So whenever we have a word problem, the method I like to use, I like to say use your DESC, D-E-S-C. The D stands for define your variable. So the very first thing we do after we read the problem is we're going to define what x and y are equal to. And we're actually going to write that down on our paper. Then the E stands for make your equations. So the number of variables should tell you how many equations you need to create. The S stands for solve, so you can solve using any method that we've talked about. And then C is complete answer. So you want to make sure that you're answering all of the parts of your original question, and that's where defining your variables is really going to come into handy at the end. Okay, let's give this a try. So this next example says, a woman rows a boat upstream, which means she's going against the current, from one point on a river to another point 4 miles away, and it takes her 1.5 hours. The return trip, traveling downstream, so that means you're traveling with the current, it only takes her 45 minutes to cover the same distance. How fast does the woman row, and what is the speed of the current? So before we even start picking through this, we can look at this and we can look at the questions to help us define our variables. So the first question asks, how fast does the woman row? So let's set that as our x variable. X equals speed, and we'll use miles per hour of the woman rowing. And then the next part of the question they ask, and what is the speed of the current? So that will be what our y variable represents. Or you could pick it whatever two variables you want. So that will be the speed in miles per hour of the current. So notice when I'm defining these variables, I'm being really specific. I'm not only saying it's the speed of what, but I'm also stating units whenever possible. Okay, so now it's time for us to move on to our equation. And to do this, we need to really understand what's going on. So let's imagine, we have a river, right? And let's say the river is flowing this way. Okay, so that means if you are the woman and you're rowing your boat, here's like her little canoe, right? If you're going upstream this way, you're actually fighting against the current. So whatever speed you're going, you actually have to subtract the speed of the current because it's slowing you down, and that will be your overall speed. So the speed of the rowing and the speed of the current are two different things that will impact the overall speed. And then if you're rowing downstream, you're rowing with the current. So the current actually makes you go a little bit faster. So your speed going downstream is actually the speed of your rowing alone plus the speed of your current. So again, to reiterate, going upstream, your overall speed is going to be x, how fast you're rowing, but minus the speed of the current. Because the current is kind of working against you. So it will affect your overall speed. But if you're going downstream, your overall speed will be the speed that you're rowing plus the speed of the current, because it's making you go a little bit faster. It's kind of assisting you along the way. So again, this is your overall speed going upstream, and this is your overall speed going downstream. So now we need to make two equations, and to do this, we can use the basic distance equals rate times time. So the distance is going to be the same for both equations. So we can say 4, because it's 4 miles. And then if we're going upstream, the overall rate is x minus y. That's how fast when you take in both the speed that you're rowing and the current, which is pushing against you. And then we need to multiply that by the time. So 1.5 hours, we could say that's times 3/2 hours. Again, this is our upstream equation for distance equals rate times time. For going downstream, we still have the same distance, but this time, remember, our overall rate is x plus y. It's the speed you're rowing plus the speed of the current, because it's actually helping you go faster. Now this time it takes 45 minutes. Let's write that in terms of hours, because we know we want our units to be miles per hour. So that's 3/4 of an hour. So 3/4. And again, this is our downstream equation. Okay, so now we can start the S in desk, we can start solving. So here, maybe I will distribute the 3 to the inside of our parentheses, and then I'll multiply both sides by 2 to clear the fraction, and then by 4 here. So if we rewrite our equations, we get 8 equals 3x minus 3y, and then 16 equals 3x plus 3y. So you can see this is actually a perfect elimination problem because our y terms are already opposite, so these will cancel out when we add vertically. Then we get 24 equals 6x, leaving us with x equals 4. And then again, we can substitute this back into either of our original equations here or here. So maybe I'll substitute into this equation. So 8 equals 3 times 4 minus 3y. So 3y equals 12 minus 4, or 12 minus 8, which is 4. So y equals 4/3. So now that we've solved, we need to go back and make sure we're answering the question fully. So they asked first, how fast does a woman row? And then they asked, what is the speed of the current? So we'll want to write this in a complete statement. So we'll say, the woman rows. And again, this is where it's useful to know what x and y represent. So you can always look back up here. X represents how fast the woman is rowing. So the woman rows 4 miles per hour. And the current, which is represented, the speed of the current, which is represented by y, is 1 1/3 miles per hour. And here we have a complete answer. Okay, let's try another one together. This is a really common type of systems problem, and it's a mixture problem with different percentages. So this says, a scientist creates a new solution by taking a 10% acid solution and adding a 70% acid solution to it. The resulting solution has an acid strength of 16% and fills 1,000 1-liter bottles. How many liters of the 10% solution and of the 70% solution does she use? So first we need to define our variables. The first thing they ask is how many liters of the 10% solution does she use? So we need to say x equals liters of 10% solution. So notice I didn't just say x equals 10% solution. It actually equals the liters of 10% solution. And then the second thing they ask is how much of the 70% solution does she use? So we can say y equals liters of 70%. solution. Okay, so now we're ready to create our equation. So one thing you might notice that we know about these two solutions is how much total we have. So we end up with 1,000 liters of the solution. So that means by adding X liters of the 10% and Y liters of the 70%, we end up with 1,000 liters total. So we can make the equation X plus Y equals 1,000. And again, this just represents the total amount of liquid. The other thing that we know about from the prompt is how much acid is in each portion of the solution. So for the very first portion, the part they started with, 10% of that, however much they had, was acid. So we can say 0.10x. And then they added this 70% solution, which means 70% of this Y liters is acid. So we can say 0.70 Y. And then we also know how much acid is in the resulting solution. So the resulting solution is 16%, which means that 16% of this 1,000 liters is acid. So we can represent that as 0.16 times 1,000. Again, a really common mistake is that people will just write 0.16. Notice the way we figured out how much acid we had here was the percentage times the amount. And then here we did plus the percentage times the amount. So on the right side of the equation, we also still need to do the percentage times the amount. And then this is the amount of acid. Okay, so now we're ready to solve. So for this, we can still solve this using the elimination method. So what I would recommend doing is maybe trying to eliminate x's. So I know that I can clear my decimals by multiplying my bottom equation here by 100 on both sides. Again, I picked 100 to fully clear all of my decimals because I need to move it, the decimal places 2 spaces over to clear all of them. And so if I do that, this is going to give me 10x. So it'd be really nice if this were negative 10x. So we can multiply our top equation by negative 10. And then that gives us two new equations, negative 10x minus 10y equals negative 10,000. And then again, this just moves our decimal place over 2 spots. So it gives us positive 10x plus 70y equals 16,000. And now you can see that our x terms cancel out, and we're left with 60y equals 6,000. So y equals 100. And then we can back substitute this into either of our original equations. So I'll choose that first equation, x plus 100 equals 1,000. So x equals 900. Okay, so now we need to make sure that we have a complete answer. So again, let's look at the question. First, they ask how many liters of the 10% solution did they use. So X represents the liters of 10% solution. So that means that they used, we can say, she used 900 liters of 10% solution. And the next thing they asked was how much 70% solution does she use, which is represented by Y. So 100 liters of 70% solution. And there you have it. Okay, so here's the last you try. Go ahead and pause the video and see if you can give this a try. Please follow all the steps we talked about. Define your variables, make your equations, solve, and then write a complete answer. All right, let's check your answers here. So first thing, notice what I did was I defined the variables. So since they asked how much did she invest at each rate, I defined X as the money invested at 5% and Y as the money invested at 8%. So you can make two equations. One is just the total amount she invested. So X plus Y is 20,000. That's how much she invested total. And then you could also make an equation for the amount of interest earned. So 5% of however much you invest in that first account is going to be interest. So you can represent that by saying 0.05x. And then 8% of however much we invested in that second account is going to be interest. So that you can represent that with 0.08y. And then the total interest that she earned was $1,180. So then again, you can solve this using whatever method you want. But you should end up with an answer where she invested $14,000 at 5% and $6,000 at 8%. And just so you know, these are really high, kind of unrealistic amounts. You'd probably never see a return like this, especially on something with simple interest. But, just for the sake of the example, we'll go with it. But just be aware this is not a realistic return with interest. Okay, that's all for today's video. Thank you so much for watching.